Sorry guys, I accidentally keluar. Okay, can we start? Very good day. Today my group 2, will be presenting about experiment 3, which is major losses in pipe. To start off, the objective of this experiment is to determine pipe friction factors or resistance coefficients. The apparatus used in this experiment can be seen. Few of the apparatus used were rotameter, tube manometer, 6-tube manometer, differential pressure sensor, digital display for pressure, pump switch, main switch, electronic pressure sensor, return hose, return valve, thermometer, gate valve, and feeding hose. This is the summary of our report. The purpose of this experiment is to seek out and establish the causes of pipe friction or the coefficient of resistance. A pipe's main losses are due to the pipe's head and pressure failure. A head loss was discussed, which is due to the inner roughness of the pipes when losing pressure. The reasons for this were some potential variables such as the coefficient of friction of pipes, volume, density of the fluid medium, and also the square of the flow velocity. Using a few formulas, which are the Moody map, the Blasius, Colebrook, and Moody formulas, resistance coefficient can be calculated. In this experiment, the purpose of the experiment is accomplished by using 5 kinds of pipes. Of all of these equations, the Colebrook equation is the most reliable. Next up is theory.
So for the theory, for turbulent pipe flow, which has the Reynolds number is between the 4,000 2 points for the horizontal Z1 equal to Z2 pi, which has constant diameter, no minor head loss, whereby the total head loss is equal to the measured head loss. So the pressure loss and the measured head loss we can calculate by using the Bernoulli equations. So for the pressure difference, the equation is equal to coefficients of pipe frictions times the length times the density times the velocity squared, then divided with the 2 times the internal diameter of the pipe. So for the measured heat loss, the equation is equal to coefficients of pipe frictions times the length times the velocity squared divided with the internal diameter times 2 times with the gravity constant. So next. So for the turbulent pipe flow, the pipe friction coefficient F is mainly depends on the equivalent pipe roughness and the Reynolds number. So this is the table for the equivalent pipe roughness of the some example of the pipes. So the equation for the Reynolds number is the speed times internal diameter divided with the kinematic viscosity. So next. So there are 4 methods to find the pipe friction coefficients. So the first one is by using a Moody check. So we need to find the Reynolds value. We can use the just now equations or just use the rho Vd divided with the dynamic viscosity. And then we need to find the equivalent pipe roughness divided with the diameter value. So by these 2 values, we can directly read the F value from the Moody check. Yes. So second, we can by using a Moody formula. So third, we also can by using a collaborate formula by using the iterations, try and error method. So fourth, by using a Blasius formula. This formula is only valid for Reynolds number is less than or equal to 100,000. So these all 4 methods can get the F value and then for calculating the measured heat loss. So next is methodology.
As for methodology, both the feeding and return holes connected to the tested pipe section. The manometer tubes at one of the two tube manometer, H1 inlet and H2 outlet, are connected to the test pipe section. The main switch and the pump are turned on. The gate valve is opened slowly until the reading of the voltmeter or actual flow meter reaches 2 meter cube per hour. The ventilation valve on the top of the two-tube manometer is opened by turning it to anti-clockwise direction to release all the bubbles it has in the system. The ventilation valve is closed by turning clockwise direction if there is no bubbles present. The gate valve is closed and the pump is turned off. The ventilation valve on the top of two-tube manometer is opened slowly until the preset minimum direction reading of two-tube manometer reach 25 millimeter for galvanized steel and PVC pipes, while 1 millimeter for copper, PVC 20 and PVC 32 pipes. Next, the gate valve is opened slowly until the level of the water at the two-tube manometer of H1 reaches the maximum while H2 at minimum. The two-tube manometer reaches temperature and actual flow rate at rotameter, which is 2 meter cube per hour, recorded. The actual flow rate reduced to 5 different values by adjusting or reducing the opening of the gate valve. The minimum value of Q actual should be around 0.2 meter cube per hour. All the reading altitude manometer H1 and H2, temperature and rotameter and the rotameter is the Q actual are recorded. The manometer tubes at the two-tube manometer transform to the differential pressure sensor P1 inlet and P2 outlet. Prior to recording the reading of differential pressure sensor, a digital display for pressure at 5 different value of Q actual at step 6. The maximum reading is 2 meter cube per hour and the 0.2 meter cube per hour. Ensure that no bubble present in the system. This could be done by opening the ventilation valve at the differential pressure sensor. If there are no bubbles present, close the ventilation valve and record the Q actual, temperature, and the differential pressure reading. All the manometer tubes were removed from the system. The gate valve closed and pump turned off before changing the feeding and returning the hose to another pipe section. Steps 1 to 7 is repeated.
Okay, for raw data analysis. Data such as internal diameter and length of pipe for the 5 pipes used for this experiment is collected. 5 tables, like the table below, is then constructed. 1 for galvanized steel pipe, 1 for copper, and 3 for PVC pipes with different diameters.
Okay, so I'm going to explain about the results and the discussion. First off, we have galvanized steel pipe. This is the result that we have for galvanized steel pipe for the temperature 31.5 Celsius. Next, this is the calculation, and from the theory that EILEEN has discussed, from the equations from Moody chart, we have the F Moody chart equals to 0.0276, and for Blasius we have 0.028806. From Moody formula we have 0.005544. From Colebrook we have 0.04324, and the average we have 0.026111. So the heat loss that we have calculated for galvanized steel pipe, we have 0.1022 meter. Next. So next we have copper pipe. For the temperature, this is the result that we have obtained from the experiment, from the conduction of experiment for the temperature 32.7 Celsius for copper pipe. Next. And this is the calculation. From Moody chart, we have 0.021. From Blasius, we have 0.0212. From Moody formula, we have 0.00318. Colebrook, we have 0.0213. And average 0.016825. And the heat loss, when the heat loss is 0.295 meter for copper pipe. Next. Okay, this one is PVC pipe for 20 times 1.5 millimeter. Okay, the temperature here is 34 Celsius, and this is the result that we have obtained. Next one. This is the calculation. From Moody chart, we have 0.0209. Blasius 0.0211. Moody formula we have 0.003786. Colebrook 0.0212 and average 0.016747. The heat loss we have obtained from PVC pipe 20 times 1.5 mm is 0.3261 meter. The fourth one, we have PVC pipe 16 times 1.8 millimeter. Okay, for this is the result that we obtained for this PVC type, a PVC pipe for the temperature 35 Celsius. Next, this is the calculation, and from the Moody chart we have 0.0269. Blasius we have 0.0276. Moody formula 0.00536. Colebrook we have 0.0271 and average we have 0.021739.5. The heat loss that we have obtained for PVC pipe 16 times 1.8 millimeter is 0.08496 meter. Lastly, we have PVC pipe 32 times 1.9 millimeter. This is the experimental result for the temperature 35 degree Celsius. Next, from the calculation, in Moody chart we have 0.0216. Blasius we have 0.0219. Moody formula we have 0.00398. Colebrook we have 0.0218 and average 0.01732. The heat loss we have obtained from PVC pipe 32 times 1.9 millimeter is 0.03871 meter. Next. So we are to compare the coefficient of friction for each of the tested pipes in the experiment, and with the coefficient from Moody chart, and to compare also the coefficient of friction from Moody chart and calculation using a formula of Blasius, Colebrook, and Moody. We are also to explain the possible reasons for the difference in their values. So for all types of pipes, except galvanized steel pipe, the values of coefficient of friction obtained from the Moody chart are the same as when measured using the Blasius and Colebrook method. There is a small difference when using the Moody's formula. This is because, according to Moody, the accuracy is around 5% plus minus for smooth pipes and 10% plus minus for rough pipes. The disparity between the values obtained from Moody's chart and Moody's formula is due to the fact that Moody reported that the accuracy is about 5% plus minus for smooth pipes and 10% plus minus for rough pipes. Next. And here we are to rank the pipe in ascending trend based on their major head loss. Okay, the lowest major head loss is the PVC pipe. With the 32 with the dimension of 32 millimeter times 1.9 millimeter, which is 0.049. The lowest, I have to cut this part. Wait. The lowest major head loss is the PVC pipe with the dimension of 32 millimeter times 1.9 millimeter. Next, we have PVC pipe with the dimension of 16 millimeter times 1.8 millimeter. And next, we have galvanized steel pipe, and then followed by PVC pipe with the dimension of 20 millimeter times 1.5 millimeter. And lastly, we have the copper pipe. When the roughness of the inside pipe wall decreases, the thickness of the slow or non-moving boundary layer of liquid decreases, resulting in the increase in flow area and the reduce in the velocity of the liquid. Thus, this decreases the major head loss due to the friction. When we refer to the Darcy-Weisbach equation, when the inside of pipe diameter is doubled, the head loss will reduce by half. However, it increases with the increasing of volumetric flow rate. Hence, when the flow rate increases, the major head loss also increase at the same time. Next. So these are the potential errors when conducting the experiment. First one, the environmental factors such as vibrations, temperature changes, and electronic noise that can influence the measurements due to the working environment. Second, we have parallax error that will occur when the eyes are not perpendicular to the flow measurement scales. Third one, when the existence of air bubbles in the tube, it will that will indicate the value in the manometer, as well as fluid leakage caused by the rubber tube not being tightly attached to the inlet and outlet valve. This all can lead to the mistake. The last one we have, when we read the Moody chart, improper interpolation between lines and points can affect the calculation. Next, we will have Divya to present.
As for the conclusion, this experiment conducted fulfilled the objective, which is to determine the pipe friction factor and resistance coefficient. As Jasmine said, there are 5 errors that we need to avoid to have a successful experiment, which are make sure no air bubble and the position of eyes perpendicular to the reading scale. Adjust the volumetric flow until it does not fluctuate or take average reading. And then and lastly the environmental factors. That's all. Next. These are the reference we use for this experiment. Thank you.
Okay.